Bismillahirrahmanirrahim. Assalamu alaikum, everyone. Today we're going to be talking about wave interactions. Okay, so we continue our understanding of waves, and one of the things that you study after you've learned how one wave can travel is you study how two waves interact if they were traveling in the same direction, if they were traveling in opposite directions, because realistically speaking, waves are not just like one single wave. There's tons of waves. If you just sit by the beach side and you watch, you'll see lots of waves traveling in the water. And so when they interact, some really interesting things happen, right? And what the picture you're looking at right now, just to make you think about this lesson here, is really quite telling. Uh, Basically, there is a light source that's been placed underneath this sheet of water, right? So this is basically a liquid. It's a water that you're looking at, and there's a light source that's underneath it, all right? Next, what we're looking at is there is a device that is causing ripples on two parts of that sheet of water. And so that first one is right over here, and the second one is right over here, right? So in those two spots, there's some kind of a machinery that keeps creating waves, and as those ripples move outwards, you if you only focus on one of these waves, you notice that there's a bit of a curvature. There's these denser spots, and then there is the spots that have no light in them at all. So what's going on there exactly is what we'll be talking about, right? But what we learn is if you now look at the other wave, as those two waves come together, when they interact, you'll notice that there's a bit of a pattern, really. It almost looks like a bit of a spider web, if you want to call it. Every single time they clash into one another, right? There is these spots that occur, right? There's these dark spots, and then there's the lighter spots, right? So these two types of patterns, they continue for that entire length over there. So this is a lab that we generally do in college, but I just wanted to show you some of the phenomenon that can occur when waves interact. All right, now the first word that you want to jot down is wave interference, and wave interference is essentially the same slide that I just showed to you a moment ago. Here's something that you could try even at home, is just put some water into like a large pan, and then poke the water at the same time at two parts on the pan. And what you'll notice is the waves, the ripples that are created by you poking the water at two different spots, it has a bit of an effect like the one you're looking at. Now, you won't see necessarily the dark spots and the light spots. That's why I told you in the previous slide, you need a light source for that to actually occur. All right? Now, in wave interference, the first thing that you want to jot down is the combination of two overlapping waves is called superposition. All right, so when we talk about the superpositioning of waves, we're really talking about two waves, and it can be multiple waves too, but basically they're coming together and they're superimposing upon one another, right? So I've got something here for you just to help you understand superposition. Just zoom into this a little bit. All right. So here are two waves, right? One of them is coming in that's red, and the other one that was coming in on the other side was blue. So there's one that's traveling right, and there's one that's traveling left. All right. And what happens is they superimpose right at that moment when you see them crash into one another. And when they crash into one another, you'll notice that the wave that had the higher amplitude and the wave that had the lower amplitude, they just added up, and they ended up being an even greater amplitude, right? So that's one observation that we see in this diagram here. But a second observation that you'll notice, though, is the waves don't crash into one another and then go back, right? They don't go back. In fact, what happens is something very cool, and I think a lot of people, they wouldn't be able to figure this out just by looking at it, is the red wave actually continues its path afterwards, and the blue wave, it continues its path afterwards with intensity and all, right? With the energy and all. It goes the same amplitude, same frequency, it just continues in its direction. So it's interesting. They even though they crash into one another, they don't change forms. They just continue after the crash, right? So this is called the superposition of two waves that are really going in opposite directions. All right. Now I want to speak to you about two kinds of wave interferences. One of them is called a constructive interference. One of them is called a destructive interference. So now let me explain to you what's going on in this picture. Number one, you want to take a look at this first wave. Okay, look at the first wave here. The one that's still, it's not moving at all, right? That wave is having a particular frequency, okay, and a particular amplitude. Now, take a look at the bottom wave, all right? Now, the bottom wave keeps moving, right? Now, what I want you to do is I want you to pick a point, okay? Just stare at a point along this wave, and you can look at where my arrow is following along. Every time that point crosses and that point right there is a crest, so it's gone now. So let me pick another one. So here's a crest. Every time that crest reaches the trough of the other wave, let me repeat, every time the crest of the second wave reaches the trough of the other wave, you'll notice something interesting that happens right below that point. So let's wait for that to happen, right? Let's wait for that to happen. So here it goes. That crest is about to come close to the trough, and all of a sudden the wave, it flattens out. This resulting wave, it flattens out. And if you're wondering how is that exactly happening, basically all you got to do is you got to add the amplitude of one wave to the amplitude of the other wave, right? And recall, an amplitude is not found by looking at the top to the bottom. What you really do is you make a line that goes straight through the middle of the wave, and you look at the distance from that line, the equilibrium line to the trough, sorry, to the crest, and then from that line to the trough. So that distance is going to be the same. The only difference is there's a positive and there's a negative. So if this bottom wave, if the second wave has an amplitude of, let's suppose, +5, then the other one has an amplitude, it has a distance from equilibrium of -5 while it's at its crest here, right? So that is why you'll notice that as soon as the trough, the +5, crosses the crest, as soon as the crest crosses the trough, right, +5, -5 respectively, you'll notice that there's a 0, right? The graph is a 0 right here, right? So as soon as that happens, you notice this very interesting phenomenon. Now, that is called destructive interference, where one wave crossing another wave destroys the energy of the other wave, right? So the crest of one wave destroyed the trough of the other wave, and they became destructive in that you had to subtract the 2 out, and you got a 0 in the end. Now, you're not always going to get 0 because it's possible to have waves of different amounts of energy, like we saw over here. Maybe they have different energies as they approach, and so, you know, in that case, there could be a constructive interference that doesn't exactly double it, all right? Speaking of constructive interference, now what I want you to do is I want you to wait till one of the crests of this moving wave is right underneath one of the crests of the other still wave, right? So let me repeat myself. You're waiting for the crest of the moving wave to be right underneath the crest of the still wave. So pretend it's +5 and +5. Well, now what happens as soon as, so let's wait for it, as soon as you notice that those two waves come together, there is a peak on this resulting graph. So it's kind of like saying 5 + 5 as opposed to 5 - 5. That type of interference is called a constructive interference because they add together to make something which is yet even larger. All right? So that's the second diagram that I wanted to share with you. Now, let's suppose that you had two waves and they were traveling in opposite directions. All right, what would that look like? Well, here it is. Now, instead of one wave being still and the other wave kind of moving along in a certain direction, here you have the top wave. Let's call that wave number one. The wave on the top is moving towards the right. The wave in the middle is moving towards the left. Now, what you will notice, it's a little hard to tell exactly where we're looking at. So what we do is we keep 2 points along this resulting wave so that we can stare at them for a little bit, okay? So let's focus on point number 1, where I'm pointing right now, all right? What's happening here exactly, right? Why is it not moving? Well, if you think about what I just told you, when two waves interact, they can destructively interfere, meaning the plus of one of the waves automatically cancels with the minus of the other wave, right? So what happens here is a phenomenon called a standing wave. And in a standing wave, every single time what's happening is if there's a positive in that first graph, right? It's just canceling out with the negative of the other graph. Let me repeat myself. The positive of one graph cancels out with the negative of the other graph, and so what you end up with getting is a 0 every single time. So this part on the resulting wave is always going to be a 0, right? It's not moving. Now, if that didn't make sense, take a look at this bottom one, right? Or take a look at the second one. Sorry, I shouldn't call it a bottom one because it keeps fluctuating, right? So take a look at this second dot. Why is this second dot going up and going down? Now, we talked about this, right? We said when two waves constructively interfere, it's going to cause the amplitudes to add up. And when they destructively interfere, that's going to cause the amplitudes to turn into 0, the resulting amplitude to turn into 0. Well, wait for, this is going a bit fast, but wait for this second dot to reach the black line right here, the equilibrium line. And every time it does that, right, every time it does that, you'll notice something is essentially what's happening is as soon as this wave is traveling to the equilibrium, there is, between the first and the second waves, however much is above, there is just much below. And because of that, they're canceling one another out. Point number 3 is notice how this wave even goes towards the bottom, right? This wave, this blue one, this darker blue one, it keeps going to the bottom. Now, how might that happen? That means there's two amplitudes that are having negative values, and because of that, those two negatives make and add up to yet a even greater negative. So that is still constructive interference. What I'm really trying to say is this point right over here, when this dark blue graph reaches this point right over here, there is basically two troughs that align, and as soon as they align, we notice that it's right over here, okay? Now, just, while we're looking at it, here's something very interesting. Now, in all the 3 graphs that I showed to you so far, all of these waves had the same frequency, right? They had the same exact frequency. This one right here is very interesting because if you look at the top one, it looks like it's a higher frequency wave, i.e. it's going up and down a lot quicker. If you look at the middle one, it seems like it's a lower frequency wave. As we talked about in the previous lesson, higher frequency, you'll notice that there's more of it in the same space. Lower frequency, you'll notice there's less of it in the same amount of space, right? And the one with the greater amount in the same amount of space is going to have lower wavelengths, whereas the one that's got a lower frequency will have higher wavelengths. Anyway, so what happens is if you were to take two waves that are of different frequencies, one is different frequency than the other, something really interesting happens. Remember, the only way that we get this third graph is just by plus and minus. That's all. You just add and subtract their amplitudes. And because the frequency is different, and they are slightly out of tune, what happens is you notice this really cool effect in front of you, right? And not just that, we actually have a name for it, and we'll definitely define it in the next chapter. But for now, I'll let you know that whenever there's a difference in two frequencies, what occurs is what we call in physics, we call it a beat, right? So more on what a beat is eventually, all right? So these two things, we've talked about this earlier, okay, in the previous lesson. Low frequency looks like this. I should have probably shown this to you before I went to that other app, but low frequency is the top type of wave, whereas high frequency is the bottom one. Again, you're just fitting more into that same amount of space or the same amount of time. All right, that's what higher frequency stands for. And at the same time as that's happening, a low frequency will have a larger wavelength and a high frequency will have a smaller wavelength. Okay? And well, that's essentially saying the same thing that I just showed you. So let's move forward, inshallah. All right, now I've really given you the whole lesson in the last 10 minutes, right? Now we're just going to really quickly run through some definitions, and then we're going to talk about something called reflection, and then we're going to talk about how to calculate things about standing waves, all right? So when we talked about constructive interference, here's what was really happening, okay? So this is a picture that's not moving, and you know what? It actually helps because the other one, it kept moving, and it is not possible for me to have paused it, but that can also lead to some misunderstandings. So what I want you to understand is in constructive interference, let's suppose, right? Let's suppose from equilibrium, this wave is 10 units, right? And let's suppose this one is 3 units. So because they are traveling towards one another, what you'll notice is the resulting constructive interference, which happens right there, is going to be 10 plus 3, which is actually 13 units. All right? And more than that, notice that they will continue, right? The large wave will continue in that direction. The small wave will continue in this direction. And that is why you notice that they did not change their forms after their constructive interference. They just continued along their very good ways. And this is still 3 units, and this is still 10 units. All right? Now let's take a look at destructive interference. Now, how does destructive interference occur? Well, you need for those waves to be on opposite sides. All right? So opposite sides means that if you look at the above side, let's call it, and we look at, we look at above and we look at below. So when we say opposite sides, don't get confused with left and right, okay? Opposite sides, essentially what that means is one is on the top side, the other one's on the bottom side, okay? They are still traveling in the same direction, in opposite directions, okay? Please realize that. So here they're on opposite sides, and they're traveling in opposite directions. Let's go back to that old wave. Before we talk about destructive interference again, let's go back to the old wave. This is considered same side. They're on the same side. They're both on the top side, okay? However, they're going in opposite directions. So you may even get a question like this in the future where it just says, if you have two waves, like it doesn't show you the picture, it just says you have two waves on the same side traveling in opposite directions. What kind of interference will occur? Automatically, you know that's going to be a constructive interference. Now, what is a destructive interference? In a destructive interference, what you will notice is, let's take those same numbers, right? Let's take this to be a positive 10 and this to be a negative 3, right? It's a negative 3. So when they two come together, when they meet at this point over here, what happens is they are going to superimpose on one another, but this time 10 added to negative 3 actually gives you 7. So this wave is only going to be 7 units high. And what they're doing is a really neat job. They're showing you the shadows of the larger wave, and they're showing you the shadow of the smaller wave for you to realize that what you see to the naked eye, what you really see, oh, that's a bad color. What you really see is this right here, and what's similar in destructive interference as was in constructive interference is after this interaction occurs, they're just going to continue on their merry ways, right? They're not going to like bounce back or something like that. They're just going to keep going, right? So this wave behavior, right, you need to learn it very well, right? You got to know what happens in which case, inshallah. Now, complete destructive interference is just one little phenomenon, okay? Think about how might that happen? How might something interfere so well that you don't see anything at all, right? You don't see anything at all, which is this blue line right here, right? Well, the way that would occur is if you had exactly, right, if you had exactly the same amp of waves, right? So if you had a wave that was positive 10 and you had a wave that was negative 10, that clearly is not to scale, and they were traveling in opposite directions, like this over here, and they had to be on opposite sides. Notice that when they come together, every part of the wave, the blue one on the top and the blue one on the bottom, is going to cancel out. And so then you would get what looks like a complete destructive interference. It's two things that are exactly canceling one another out. And a little bit more on that, there is a possibility, there's a way that you can do this. If you took two of exactly of the same speakers and you pointed the two speakers in a direction that was geometrically exactly the same, and you went and you stood in a certain part that both of the sound waves from that speaker are traveling, what's very interesting is, in fact, they would destructively interfere, and to the point where they would be completely destructive interference, i.e., you wouldn't even hear a sound there. No matter how loud somebody makes it, no matter how much they increase the amplitude of both speakers, you won't even hear it. It's quite something, okay? So that's complete destructive interference. Now, we're going to talk about a second kind of behavior. So first we talked about wave interference, that what happens when two waves hit one another. Now we're going to talk about a different behavior, which is called a reflection. Now, for reflections, when we study these, you need to remember two things. Number one, you need to understand that you can have either a free boundary, you can have what we call a free boundary, okay, so right over here, free boundary, or you can have a fixed boundary. Now, what's the difference? In a free boundary, pretend that this piece of rope, right, this piece of rope that's been tied along the pole here, it's allowed to move up and down. Okay, it's allowed to move up and down, meaning it hasn't been tightened around it so hard that it can't even move, right? So what happens is there is a wave, right? A single wave, right? A single wave travels. You're going to need to know this really well as we move into the next chapter. This wave is traveling, and specifically, if you remember from the previous lesson, this is actually a pulse because there's just one, right? It's not a periodic wave. This is the pulse, right? We send a pulse down this rope, and as we send a pulse down this rope, it's going to hit, right? It's going to hit this reflected boundary, right over here, and specifically that's called the reflection. And what happens is the energy that this pulse was bringing, it transfers to the end of that rope. And what happens is the rope, it actually ends up going upwards, right? So observe carefully. The rope was over here, and now the rope is over here, i.e. it traveled, which way, where should I draw this? So it traveled upwards, right? It traveled upwards. Now, what's going to happen is something even more interesting. That incident pulse, right, was energy, right? Amplitude is energy. It's actually energy squared. The energy was transferred to the pole. Well, guess what? Now that energy is going to transfer back the other way. So what you'll notice is that same blue dot, right? Now it's gone down. Now it's gone down. So it's using that free boundary to reflect off of, and it reflects and it goes back. Now, one thing you do want to remember is as it goes back on the same side. What do I mean by that? Notice how the incident pulse was on the top side. The reflected pulse is still on the top side. That's going to matter in a moment, okay? Now, what if, on the other hand, we were to fix the boundary, right? We were to fix the boundary. Let's look at that same exact graph, the incident pulse. So it comes in, all of that energy goes into this fixed boundary. Maybe it's a wall that it's connected to by some screws or whatever it may be, but it runs into this fixed boundary right over here, and you'll notice is that wave, right? That wave, it actually reflects, right? It reflects and it moves back. But what do you notice is so different now as how it moves back from before, right? Look at it carefully. What you'll notice is now it's actually on the bottom, right? It started on the top right here, but now it's been reflected to the bottom. And so what we would say is what's so different about it is now it's on the opposite side. All right, so that's the difference between a free boundary and a fixed boundary. All right, the word that is used is the word inverted. Okay, when you go from the top side to the bottom side, we say that the wave was inverted. Now what I'm going to show you here is going to help you see this happen in real time. Okay, so watch carefully as I go through this, inshallah. What I'm going to do here is I'm going to send one pulse. Okay, I'm going to send one pulse over to a fixed end. Okay, actually, let's go loose end first. Okay, so in the previous lesson, if you guys recall, when I was teaching you just about waves, all I did is I made it a no end, and I just sent a pulse down this wire. Let me make it slow motion. But I sent a pulse down this wire. I said, see, this is how waves travel. They travel in a, this is called a transverse wave, recall, because each particle simply goes up and comes back down, while at the same time, the wave is propagating towards the right. Let me shut off the damping here, right? So there you go. Now there won't be any loss of energy. So the amplitude stays the same the whole way. So the wave is traveling towards the right, but each individual particle is going up. All right, so that was the previous lesson. So in this lesson, we're going to, let's start with loose end, right? In this loose end, so there you go, you got this this pole, and this piece around it is not tied to the pole, right? So what did we learn in that previous slide? We learned that what's going to happen is this pulse that we send is going to go down this wire, or whatever this thing is, and it's going to come back through the wire, and it's going to come back on the same side. If it traveled on the top, it's going to come back on the top, right? So go ahead and observe. And all that energy is transferred over to the pole, which transfers it back, and we've got something that's coming back this way, right? Now, please ignore what happened afterwards, because that is it's kind of a little bit complicated. So only look at the example right up until here, okay? Now, you will understand why that other phenomenon happened when I show you fixed ends. Okay, so let's reset this. Okay, let's restart this. And this time we've got an end that's fixed. So I'm going to send a pulse down this wire, and we know that it's going to get inverted as it comes back, and so it comes back this way. Now notice how these are both fixed boundaries, right? They're both fixed ends. So what will really happen is every time it goes back and it hits this fixed boundary, well, it's just going to get inverted, and it's going to come back up to the top, and it's going to go back, all right? So that's the difference between free boundaries and fixed boundaries, and when a wave is reflected. All right, now this is arguably the most challenging part of the lesson, so you want to pay very careful attention. This is a phenomenon called a standing wave. Okay, it's called a standing wave. All right, so standing waves, first thing that we'll do is we'll watch a little video on standing waves, and I found out later that in fact you guys can hear the volume. So I'm going to shut this off, all right? It says initial wave group of 0.6 hertz. Now I hope that you're looking at that and you understand that terminology. So that's the frequency of this wave, right? That's how much of it happens per second. Think of it that way, right? So 0.6 per second. And wave height of 4 inches. So if you think about what is wave height of 4 inches, that means the amplitude is 4 inches. Okay, so what we're looking at is a particular frequency and a particular amplitude. So that right there is it's just a wave, and what you'll notice is there's a boundary at that far end, and there's a boundary at this end over here, and that's really where it all starts from. Okay, a standing wave occurs when you have two boundaries that are essentially fixed. All right, and now you guys will notice that after they modulated that, right, you'll notice that it looks like there's just something skipping along in this water tank, right? So what they have created is a phenomenon called a standing wave. All right. Now that doesn't make complete sense until you don't see a few diagrams. All right. So what they're doing here is they're making different kinds of standing waves, and here is a different angle of it. All right. So that's a standing wave that's occurred. What's basically happening is they sent waves that were sent forward. Okay, they were sent forward, and they were waves that were reflecting. Remember from that previous section about reflecting waves, and they're inverted, so they go below. And when they do that, the ones that are coming above and the ones that are going below, they either add up or they subtract out. And what happens is you have what's called a standing wave. All right. Now, the description of it is really not just enough. All right. There's different kinds of things that you can do to try to understand this. So here, recall the waves are on a fixed end. And if I turn this into oscillation mode, what I want you to focus on is take a look at this wave as it travels. Where is it going to go? And I want you to think about what we just talked about, right? So as it's going to go, it's going to reflect off of this boundary, and it's going to come back. Now, if you're thinking, why are you talking about reflected waves still? It's because that's how standing waves occur. They occur through a reflection, all right? So here goes. That wave is going to hit, and take a look at what happened. It went below, right? It went below. Now, so now there is a wave that's trying to get to the other side, right? At the same time that there are waves that are traveling forward. And so what ends up happening is exactly what you guys saw in the water tank. You're looking at some bit of a standing wave, even though still there is a slight difference in this. It's not exact. And to make a standing wave occur just perfectly, you need to have the same thing going in the top as what is in the bottom. If you can manage to do that, then you essentially have a standing wave. This at the current isn't exactly a standing wave, but it gives you an idea of this pattern that you guys saw in a standing wave. All right, I'll show you a few more things, inshallah, about this over here. So let's first talk about what a standing wave is officially. So it's a wave pattern, okay? It's not a new kind of wave. It's not like there's transverse waves, there's longitudinal waves, and then all of a sudden there's a standing wave. No, a standing wave is something that happens to a wave, okay? So a standing wave is a pattern that results when two waves of the same frequency. This is really important for you to remember what causes this to happen. It's a bit of memorization, really. So you'll have two waves that have the same frequency, and therefore they also have the same wavelength, right? But at the same time, they have the same amplitude. And finally, they travel in opposite directions, all right? So frequency is same, wavelength is same, amplitude, they're all the same. The only difference is one is traveling this way, the other is traveling the other way. And when that happens, as soon as that phenomenon happens, what you have is something called a standing wave. Now, there are a few things that you must know about a standing wave. All right, there's a few things you need to know about a standing wave. The first thing that you got to know is called something that it's something called a node. All right. So a node is a point in a standing wave. So now we've gotten past the point of talking about standing waves. Okay, so when you're looking at a standing wave, it's the point that has zero displacement. So let's pause here. All right, when did we last talk about zero displacement? Right? So back in this diagram that I had earlier, right, we talked about when there's a destructive interference, right? When there's a destructive interference, right that point over there, notice how every single time it's always stuck at the same exact spot. So this makes this point a node, all right? That right there is a node. But if you look along this wave, there's a node right there, so that's one node. This is two nodes, that's a third node, fourth node, fifth, and sixth. They're not going anywhere, right? So there's 6 nodes in this wave, all right? And again, they're the points where there is complete destructive interference right at that point right there, right? Which is causing zero displacement. Now, take a look at these 4 standing waves, all right? These are 4 standing waves. And if you're wondering, how can you make them look like that? Basically, just keep changing the frequency. I have something in the lab that we would have played with, but if you keep increasing the frequency, it's just a knob, okay? You just keep turning the knob, and as you make the frequency higher, you cause more of these to occur on the wave itself, okay? Just think of it that way, all right? If that doesn't make sense to you, look at it like this. In this situation, let me just go ahead and restart this. In this situation, if I were to make the waves of higher frequency, right, you just kind of see them traveling like this over here, okay? These are just waves of the same exact frequency, and they're just traveling. That's all you understand about it, right? And if you think about destructive interference, right? Now here's that standing wave that's starting to look like it's coming to. Right? Let me pause it right here. So that's a perfect standing wave right there. And notice how the green points, the red point, right? They're exactly in that same spot. They're not moving at all, right? They're your nodes, right? Now, back to this over here. Let's talk about an antinode, right? An antinode. Oh, wait, 1 second. Let's label the nodes, okay? So in this first one, all right, those are the ones, the nodes. I've labeled them in yellow because this is on black background, right? Here, there are 1, 2, 3 nodes, right? In the next one, there is 1, 2, 3, 4 nodes. In the next one, there are 1, 2, 3, 4, 5 nodes. All right, so that's one thing to kind of just look at, right? Now, there is something else called an antinode, right? There's something else called an antinode. Now, what is an antinode exactly? That is the part that is halfway between the 2 nodes. Okay, so find a point that's halfway between the yellow node and the yellow node over here. You'll notice that that point right there, right, that is the antinode. So we normally call the nodes ends, and we call the antinode the letter A. And what you'll notice, just as the node was not going anywhere, it was stuck exactly where it's supposed to be, an antinode is the thing that's traveling the highest and the lowest, right? So in this situation, this second dot that you keep looking at going back and forth, that's the antinode. It goes to the highest and it goes to the lowest. So if an antinode is halfway between a node, what you'll notice is this second wave has 2 antinodes. All right, it's got 2 antinodes. This third wave has 1, 2, 3 antinodes. This fourth one has 1, 2, 3, 4 antinodes. So one thing that we quickly realize is this one has how many nodes? 2. And how many antinodes? It's got 1 antinode. This one has 3 nodes and 2 antinodes. This one has 4 nodes and 3 antinodes. This one has Bismillah. 1, 2, 3, 4, 5. So 5 nodes and 4 antinodes. So you'll notice that every single time you basically have one less antinode than the number of nodes themselves. All right. Now, the last thing that we want to talk about in this lesson, all right, the last thing that we want to talk about in this lesson is a very confusing one, right? So if you're doing something else at the same time as watching this, you want to kind of pause for a little bit and take a look at this slide over here. What we need to do is we basically need to relate the what do you call it? The wavelength of the wave itself, all right, the length of the wave and the length of the string, all right. Now we're going to take a look at the length of the string, and we're going to take a look at the wavelength, all right. So those are two different things. L stands for the length of the string, all right. I don't want you to get confused by these two. So it's the length of the string. Whereas lambda stands for wavelength. Okay, so the length of the wave. So once that string gets all bent, you know, in the shape of a curve, that it would be a wavelength. Now, a wavelength, recall, okay, if you forgot from before, I understand, no problem. We'll go over it again. A wavelength is measured by looking from either a crest to a crest or from a trough to a trough. So if this is the wave that we're looking at, you can either look at this distance and call that the wavelength, or you can look at the distance from a crest to a crest, which is right over here, and you can call that your wavelength. But what we're going to do is we're going to pick a slightly different point today, and the point that we're going to pick is completely valid. It still gives you the same length, by the way. It's going to be from here to here. Okay, we're going to look at that as your wavelength, because if you think about it, wherever the way you measure a wavelength is when it completes its cycle, right? When it completes one cycle, you stop and you measure the length, right? So we go ahead and we start from this point, which isn't necessarily a crest or a trough, but it's a nice point to start from, because a sine wave looks like that, and we stop right over there again. Okay, so we're going to be focusing on the length of the string and the length of the wave, and the relationship between them. Now, this is not in the textbook, okay, so you have to know this separately. The relationship between them is that the wavelength at some variable n, at some integer value of n, is 2 divided by n multiplied by the length of the string. I know that looks like a very weird formula, but I will help you try to put that all together, inshallah, in just a moment. All right? So what you want to do is you want to think of this as a table. All right? It really helps. All right? So in this table, what I'm going to do is I'm going to write down nodes. I'm going to write down antinodes. And I'm going to write down, Bismillah, wavelength. All right? So we're going to kind of go through this and see how things change, Bismillah, as inshallah we go through every single one of these diagrams. So I'm going to try to keep it so that every single diagram that they've given us, they provided us 4 diagrams, and we certainly could make more if we wanted, or we might even make more if we get some time left in this video. Okay, so let's go to we're gonna leave this first box empty because it's not a wave yet, so it doesn't make sense to say anything about it. Let's go to this first standing wave. Right, we'll look at the first standing wave. In that first standing wave, notice how it's got 2 nodes, it's got 1 antinode, and according to the formula, the wavelength is equal to 2 divided by 1 multiplied by L. Now, if you're wondering where exactly did I find the number 1 from, okay, so that's a very good thing to think about right now is the 1 is from the part of the antinodes. This is where you get that 1 from. Okay, so that is where the 1 came from. Not the number of nodes, right? Because I know n sounds like nodes, but this is where we get the 1 from. It's really from the antinodes, right? So what you can conclude is lambda is equal to 2L. Now, what exactly does that mean, right? What does that exactly stand for? Well, here's what we're talking about. We were looking at a wave, a standing wave that looked like this, right? And what we just came to the conclusion is we came to the conclusion that lambda is equal to 2L. All right, now what exactly does that stand for? First off, please realize there's a wave that's going forward and there's a wave that's coming back the other way. They have the same frequency, they have the same wavelength, they have the same amplitude. So for this standing wave, what we're saying is its wavelength is actually twice the length of the string. Recall that the length of the string was from here to here. That was the length of the string. But what we're saying is if you wanted one wavelength, this is not one full wavelength. This is actually only half of a wavelength. A complete wavelength, recall, it's supposed to look like this right here. It's supposed to go to the top, come back to the middle, go down, and then come back to the middle again. This one has only gone half the way. It's gone to the top, and it's come back to the middle. We need it to technically go like this, and then come back. So what we're trying to say here is the following. We're saying that if you want to relate the wavelength to the length of the string, right, the wavelength is actually twice the length of the string. That's what we're trying to say, all right? So I know that first diagram is confusing, so feel free to watch this a couple of times to understand it. So this formula is not in the book, but it's really handy because it helps us figure out exactly what the wavelength is based on the length of the string that they provided. Okay, let's do the next diagram, all right? In the next diagram, count the number of nodes, all right? So there's 3 nodes. Count the number of antinodes. There's 2 antinodes. According to the formula that we developed over here, lambda is equal to 2 divided by that number right there. And it's always 2 divided by, okay? So 2 divided by 2, and then it's multiplied by the length of the string. Now if you do the math, you'll realize that 2 divided by 2 is 1, so lambda equals L. For this, I don't need to make a separate diagram. What it's trying to explain to you is the following. It's saying that one wavelength is equal to the length of the string. So take a look. The sine wave goes up, comes to the middle, goes down, and then comes back to the middle. That is one complete wave based on our definition of how much one wave should be. And so what we're trying to say with this formula written in black is the length of the string and the length of a wave are exactly the same when you have this situation occurring, when you've got 3 nodes and 2 antinodes. All right, let's do one more diagram and we can, continue to do more, but I think this should get the point across. So count the number of nodes, right? Count the number of nodes and you have, bismillah, 4 of those. Count the number of antinodes and you've got 3 of those. Apply into the formula, so lambda is equal to 2 divided by 3 times the length. And so this time it doesn't simplify, it just says that lambda is equal to 2/3 L. What does that mean exactly? All right, so if we go back to the diagram and we try drawing one wave, right, one wavelength. A wavelength looks like this right here. Notice that we have completed one wavelength, right? That is one wavelength. But guess what? It's exactly 2 out of 3 parts of the length of that string. You see? So the length of the string was L, but we only need 2/3 of L to complete one wave. So that's the difference between saying what a wavelength is versus what the length of the string here is. A wavelength means how much of that string do I really need to create a sine pattern like this over here. Okay, so that's how you connect the Bismillah, the wavelength and the length of the string to the two. Thank you so much for listening. This video has gone quite long. The homework for this section is, of course, going to be up online, inshallah, in detail. And so you guys, please complete that and then submit it. Thank you and Assalamu alaikum.